folks. In this lecture, we are building a problem-solving strategy that we can rely on when faced with quantitative problems. Now, if the strategy I outline here doesn't make sense to you, most modern chemistry textbooks will have a problem-solving strategy which might appeal to you more. No matter what process you choose to use, it's very important for you to make an effort to develop a methodical thought process when working with quantitative problems. It'll make your life much easier, believe me.
In the first part of this video, I'm going to demonstrate a problem-solving strategy I use and then condense all the steps of the strategy in a review slide at the end. We begin with the problem statement or question. Now here's a problem that I found on the web. How many seconds does it take light to travel to Earth from the nearest star, Proxima Centauri, which is 2.5 times 10 to the power of 13th miles from Earth? Now at this point, it's important not to panic. It's natural to feel trepidation when facing quantitative word problems, but the most important and interesting problems we will face will be, at first glance, complex. So how do we face multifaceted problems and overcome them? I try to keep two sayings in mind. The first is a quote by Francis of Assisi. Start by doing what's necessary, then do what's possible, and suddenly you're doing the impossible. This saying reminds me to work my problem-solving process. The second is a very old proverb. How do you eat an elephant? Well, one bite at a time. This one reminds me to break the problem down into smaller bits. It is critical to have a process and strategy for solving problems so we can do what is necessary and possible. When we break a problem down into small, manageable bites, we are striving to break down a large, complex system into smaller problems that can be readily answered by simple, fundamental science. The alternative is this, to simply wait around for insight to just spring forth and solve problems for us, which usually means we'll be waiting around for a long time to get anything done. Reliable occurrences of helpful insight tend to happen more frequently within a methodical thought process than from a mental vacuum. Let's begin building a robust problem-solving process. First, I read the problem carefully and write down the given information in the problem statement. I will also write down any scientific information, equations, or formulae that I remember or find in my notes and textbook that might be relevant to the solution of the problem. I often do this on some scratch paper. The act of writing all the information down ensures that I've identified everything that the problem has to offer. In this problem, the obvious piece of information gathered from the problem statement is the distance between the Earth and star, 2.5 times 10 to the power of 13th miles. As I read the problem, somewhere in the back of my mind, the concept of the speed of light crops up. Now that could be important, so I look it up and write down the speed of light constant too. Next, I want to determine the best starting point, which is usually some information given within the problem statement, and determine the end point, which is the goal or answer that the problem requires. Most of the time, I write down the end point first. It's usually easier to identify. In this problem, we are asked to quantify the number of seconds it will take for light to travel from the star to us. This is the end point. The only given information I found in the problem is the miles to the nearest star, so I guess that will have to be the starting point. If I can, I try to guess just how big or small the quantity of the result will be. I do this so I have some idea of what to expect at the end, and some way to judge if my result makes sense. I know that our nearest neighbors are light years from us, so I'm thinking I should get a pretty large number at the end of this computation. There are a lot of seconds in a year. Now I map a solution path from the beginning value with units to the end value with units, making sure to take only one step at a time. Each step needs to represent a single conversion relationship or equation that connects the two units. I'm not thinking about numbers, just units and how they might be related to simple single unit conversions, formula, or equations. Looking at my list of information, I quickly see I have the speed of light in units of meters and seconds, and that is the critical link. It is providing a conversion relationship that can bridge the gap between length in meters and time in seconds. We see that the list of information I wrote down in the first step provides the insight I need to solve the problem. So all we need now is to fill in the small gaps in the map between miles and meters. Conversions between the length in U.S. customary units to a length in SI units should be easy to find, I would think. At this point, we go out and find quantities we need and list the specific conversion relationships, formulas, and equations that are required in our solution map. We want to keep track of the sig figs of each of these quantities. Now we already have the speed of light. Now I need a conversion factor that relates miles and meters. Oh no! I don't have this conversion. You see, this might be a common hindrance if you were, let's say, to find yourself on a deserted island with nothing to use but your trusty chemistry textbook. Or a more relevant circumstance would be if you find yourself in the middle of an exam where you have just the information in your head and the bits of data the professor deemed worthy to put on the test. After thinking a short bit, I realized that I'm being asked to go from the U.S. customary length, miles, to an SI length in meters. I need just one relationship to accomplish this, to cross these two unit systems. For this problem, I'm prepared. I have memorized, probably because some teacher in the past made me, the conversion relationship of 1 inch equals 2.54 centimeters, along with plenty of U.S. customary and SI unit conversions that I can insert in between. This should finish the job. All that is left is to tweak my solution map and list all the conversion relationships I will need at each step. So now our path is miles to feet to inches to centimeters to meters to seconds. Only the last conversion on the list is not exact. Though not required in this problem, many times we will need to utilize scientific equations, formulas, and/or chemical reaction equations to identify complex relationships between units or to produce specific derived units. For example, an equation would be required if we wanted to take a given temperature value in Fahrenheit and convert it to an absolute temperature value in Kelvin. As we get on in chemistry and face more elaborate problems, scientific equations, formula, and chemical equations will show up on our maps, filling in some of the gaps between our beginning and ending points. About here is when I will adjust any conversions to more appropriate sig figs to save time when I input them into my calculator. I'm too lazy to type the whole speed of light conversion into my calculator, and frankly, all those additional numbers will do nothing for the answer once it's adjusted for sig figs. In the problem statement, the given information only has 2 sig figs, so 3 or 4 sig figs on the speed of light value should be adequate. So I will replace the old speed of light conversion relationship with 2.998 times 10 to the power of 8th meters, which is 4 sig figs, equal to 1 second, which I will say is exact. It's time to convert my map to a series of ratios or conversion factors and set up any equations or formulae that I might need with the proper values and constants. Using my computation map, I set the ratios in a configuration that when I multiply them, the units in the numerator, shown as the next unit in the solution map, cancels the preceding unit in the denominator. I also plug in the numbers using the conversion relationships in my list. If we're utilizing equations and formulae, it is important for the units to cancel within them so they produce the units we desire in our overall computational scheme. It is at this point when we can finally do the computation. In more complicated calculations, I may have to keep track of the sig figs between steps if needed, using underlines. Remember, we don't round off between intermittent steps, but we do preserve enough digits at each step to avoid producing round-off errors in the final number. Rounding off is not as much of a problem as it once was, since modern calculators can store everything as we go. Even so, we still have to keep track of the sig figs at each step. All right, look at that baby my calculator just produced. Now it's time to round off our computed value to the appropriate sig figs and make sure that we have units appended to the answer. In a calculation like this, which is just a simple series of multiplication-division computations, figuring out the sig figs is quite easy. All we have to do is look for the number in the computational chain with the least number of sig figs. This number will typically be the measured value at the beginning of the chain that was given to us in the problem statement, but not always. So at the end of this computation chain, we obtain a final value of 1.3 times 10 to the power of 8 seconds. One last thing. In some way, we want to highlight, mark, or box the answer so anyone looking at our work, including ourselves, can quickly find the answer. Now, this next step is often ignored, but it is very valuable in getting the most information from the computation. We need to analyze the result, asking ourselves a series of questions. Is my final answer what was desired and what was asked for by the problem statement? Well, the problem wanted the final answer in seconds, and sure enough, we got seconds. Does the result make sense regarding the magnitude we expected for the answer? Well, we expected to get a large number for this computation since the star is such a large distance from us, and it should take a considerable amount of time for even light to get there. It might be prudent to do a little extra work and figure out how many years this value represents and see if we are in the right ballpark. I would think the answer should be a few light years. And we see that our answer in seconds is equivalent to 4 light years. Not bad, I think. Check. One more time. Does the result have the correct number of sig figs and include the correct units? Missing units in an answer is one of the great sins in computations. Without the units, we don't know what the result is even meant to represent. And we also know we'll have points deducted if we have 12 sig figs when it's clear our answer should only have 2. Getting the sig figs wrong means we're representing the precision and error incorrectly. To a scientist, that's almost as bad as flubbing up the computation and getting the completely wrong number. Finally, is there anything more we can learn from this problem that we didn't know before? Problems are not meant just for practice, but many times can teach us more about the science. Maybe there was a math trick we discovered that was handy, or maybe we learned an important scientific concept that wasn't in the chapter text or lectures. Maybe we simply were surprised by the result. In this case, I didn't know that Proxima Centauri was the closest star. I always thought Alpha Centauri was the closest star. Turns out, after looking on the web, that Alpha Centauri is a triple star, and Proxima Centauri is the closest of these 3 stars. I also allowed my mind to wander a bit and think about the day when we would have enough science to one day travel to stars multiple light years away. At first, it probably would take many years in a spacecraft to get to Proxima Centauri, and I was thinking how embarrassing it would be if we sent an ark or cargo ship with thousands of souls suspended in some sleep stasis during the trip to establish a colony on a planet a few light years away using light sails or some other slow travel tech taking many years to get there. And just how pissed off all those people will be when they find people already there because we figured out on Earth during all that time they were asleep how to use a wormhole or quantum anomaly to get there in just a few days. The next step is so very important for us to consider in our process. What if we didn't get an answer or we just got a wrong answer? Well, we want to be sure that we have documented the problem well enough so we can identify where in the strategic process we got hung up. This documentation will make it faster to finish the problem if we gain some insight later. At the very least, we now can form very specific and effective questions that have a greater chance of being answered when we go get help from our teachers or tutors. It can be frustrating to a teacher or tutor when someone comes to work a problem and the page is absolutely blank. Work the process. Teaching and learning are much more efficient and effective when we use a process to help guide us to points of misunderstanding. With a process, we now have a tool to help us identify where we might have gaps in our knowledge. As promised, here is the outline that summarizes all the steps in this quantitative problem-solving strategy. You might ask, hey, do you really go through all this when you work a problem? Well, after working so many problems for so many years now, much of this problem-solving process is reflexive and instinctive. I don't consciously need to write as much down as I once did. And frankly, many problems usually can be solved in 1 or 2 steps, so there is little worth in the effort of creating the map. But when faced with a truly difficult puzzle requiring many steps, or when I'm teaching things to students, I will work the process as diligently as I can. It is a valuable tool to use, and who knows, maybe someday when faced with a very important problem, it will help us make the impossible possible. Catch you later.